I wouldn't mind being the next YouTube sensation, strictly from the standpoint of I'd like the money. But that's okay. Although I don't think it really counts. I don't think it really counts if I'm doing it for work. I don't think I can collect it up. Okay, piecewise functions. That's what we're dealing with today. Parent functions, piecewise functions, and transformations. Now, we may or may not get through all the notes today. If we don't, not a big deal. We'll just finish them up tomorrow. Not a problem. First part is piecewise functions. Piecewise functions are different equations on different parts of the domain. All it means is that if we have a function that is defined differently depending upon where you are. Okay? That's what a piecewise function is. Where we are in the domain determines what function we are particularly using at that time. This is extremely useful. One of the most common uses when you get to calculus is you cannot do certain things to absolute value in calculus. You can't. So what do? We rewrite the absolute value equation as two separate equations. The absolute value of x is equal to negative x when x is less than 0. It's equal to x when x is greater than 0. We take it down and break it into two equations. We analyze this equation, we analyze that equation. You can do that. Absolute value actually breaks up very easily into two separate equations. Okay, that's what a piecewise function is. You're breaking it apart. Now, in examples we have here, we have two equations. When x is less than 1, our equation is x squared. So everywhere less than 1, we have x squared. Okay. When x is between 1 and 4, it's x plus 2. Something like that. So it depends upon where we are in our domain, what our equation looks like, which function we are using. That's what a piecewise function is. So if I were to combine these two into one, so it would look like this from here. And let's see. And look like that there, although that's gone too far because it ends at 4. Yeah, that one does end at 4. Okay. Sometimes piecewise functions are connected. Sometimes they're not. Okay, you might have a line, a function that when you look at the graph, it's a half circle here and a straight line there and a straight line here, and here's a curve. Doesn't matter. Piecewise function is for different places. We use a different equation to describe, but it is still considered one function. X squared, when my domain is less than or equal to 1. X plus 2, and I didn't actually do this right. I should actually have an open circle here, closed circle here at the end, and a closed circle here. When you have a piecewise function, the domain only has one function for each point. So you'll notice here it's less than or equal to 1. If I get 1, I'm doing x squared. Anything larger than 1, I'm doing x plus 2. At 1 itself, I have to do one or the other. It cannot be both. It's not a function if it's at both. So if the lines don't connect up, you're going to have an open circle at one of the ends. Okay. Questions so far? And you can have lots of parts for an equation. I've seen some really big ones where, okay, from here to here it's this, from here to here it's this, from here to here it's this, from here to here it's this. This covers my domain that I'm talking about, different parts of the domain. What's the domain of the whole function? What's the smallest possible value of x I can have? Negative infinity. How large can I possibly be? 4. So my domain of the entire function is from negative infinity to 4. Okay. That's my whole function, but I have part of it's described this way, and part of it's described that way. Okay. I have a huge domain for the whole function. Part of it's one way, part of it's another one. That's what a piecewise function is. You're breaking it down into pieces. Okay. This is extremely useful in issues like this. Okay. So, if I have, for example, this is a perfect piecewise function. Depending upon where I am, determines how much I pay. Often it's done by businesses. When you're purchasing items, if you buy 50 or less, it costs you so much. If you buy in bulk, it starts costing you less per amount, right? That's a perfect piecewise function. Perfect piecewise function. When I get above a certain amount, it costs this. So, an example here, this is a perfect one for a piecewise function. So my function f of x is equal to, and we use a piecewise function, we have a bracket, a one-ended bracket. Those are all the parts. Okay. So my annual income is less than $2,000. Does that include 2,000? No. How small can I get? 0, right? I can get 0 income. I can't have negative income. Well, yeah. So my income is from 0 to 2,000. How much taxes do I pay? 0. So my function is 0 when I make less than $2,000. So if my income is between $0 and $2,000, my amount that I pay is 0. I don't pay anything. Okay. Now, my next one. What's my next step in my income for tax purposes? 2,000 to 6,000. Okay. So 2,000, is 2,000 included or not included in the next one? It is included because it wasn't included in the one before. So I have 2,000, and then I have 6,000. Now, is 6,000 included or not? Yeah, because it's over 6,000 in the next one. So it is included here. Okay. So any money I make between 2,000 and 6,000 inclusive, how much do I pay? 2%. 2%. So that would be, how would I figure that out? 0.02 times x. 0.02 times how much money I have. 2%, right?
2% of 2,000. Yeah. So it's 2% of income that's over 2,000, with 2,000 not being included.
Well, 2,000 is not included here. It has to be included in one of these two.
Okay.
Because what if I made exactly 2,000?
Yeah.
What's the IRS going to do? They're going to make me pay. Okay? Because they said, hey, you make less than 2, you're here. You know, you make $1,999.99. You pay one thing, although they do make you round up everything nowadays, so that really sucks. Okay, but it is that point, what are you going to have to be at? And you do have to make that decision. Here, I would make the decision 2,000. Okay.
Is this like accurate?
No.
Oh, okay, cool.
No. Although generally speaking, if you're making less than $2,000, you're probably not going to be paying in a year. You're not going to be paying any income tax. And even though you may have taxes withdrawn from your paycheck, you'll get it back when you file your tax form. You'll get it back. And pretty much, if you're making less than $6,000, you're going to get it back anyways, more than likely as it is. Okay.
So we're making like 6,000.
Okay. Now, so my next one is income over $6,000. So as long as X is larger than $6,000. Okay. So now I've covered all my bets for what my possible income could be. From making nothing to making lots and lots and lots of money. But my equation changes each time. My equation on the next one is I play $80 plus 5% of my income. So I pay $80 no matter what. Plus 0.05x. This is a great example of a piecewise function and where piecewise functions fit in reality. When it's broken down by, well, between here and here you have a certain rate, between here and here you have a certain rate, between here and here you have a certain rate. This is a perfect example of when a piecewise function is really applicable. Okay, it's one of those ones. It's a great real life. Are those accurate numbers for taxes? No. It does kind of do that a little bit. If you've ever filed your own taxes, okay, tax tables. They actually have tax tables, and you find your income in the tax tables, and it'll say between here, if you make between this much and this much, this is how many taxes you owe. So it is a piecewise function. Between when your x is between here and here, your income is between this number and this number, you do it. However, those numbers are like $500 apart, and it starts at 0 to like more than 300,000 or some crap like that. So you've really got pages and pages and pages of what could best be described as a piecewise function. Okay, it's huge. It's not really all that efficient way to do it, but that's okay. I'm not in charge. Okay. But yeah, this is, like I said, this is a perfect example of where it's applicable to create something. Okay, this is a good application of it. Okay. They are useful for a lot of things. And like I said, sometimes when you're working an equation, breaking it down into parts and doing it, okay, one part can be described by this equation, one part can be described by this equation, one part described by this equation, and then you work with each one separately, it really works out pretty good.
Wait, do we need to write a domain for that?
That was, okay, good question. I have my domain on here.
So we don't.
My domain, this is the domain right here, this stuff here. That is my domain right there. Okay. Now, the only reason I did it on the previous one was to explain, hey, I have this actual giant domain for the whole thing, but I'm breaking it down into parts. When you're writing a piecewise function, this is my equation right here. This is the domain for each portion. This is the domain for the whole thing. This part of my domain, I pay nothing. This part of my domain is 0.02. This part of the domain, it's 80 plus 0.05. Okay. So each part of the domain does it. This whole thing is my domain. I just break it down into parts depending upon what I need to do. Okay, transformations. Taking a graph and moving it up, down, sideways, back, forth, making it fat, making it skinny, all that good stuff, making it go up, making it go down. Transformations. The more you understand transformations, the more that looking at an equation, you can figure out what's going on with the equation just by kind of looking at it without actually having to graph it. So, vertical transformations. I take the function and I add some constant. C is a constant. So x squared plus 2. X squared minus 5. Okay, that's taking a function and adding something to it. Okay, that gives us a vertical shift. Yes? No, that just means the whole thing moves up or moves down. So, if I have x squared plus 1, that means I just take my parent function of x squared and I just move it up. Okay, if I have absolute value of x, absolute value minus 2, that means I take the absolute value v and I just move it down 2 units. So your vertex is what's changing on those. Okay. Now, it might be the entire function. If we have a complex function, the whole thing shifts up and shifts down according to what I'm adding or subtracting outside. If we're doing logarithms, the log of x plus 2. Ooh, that means I take the graph for logarithm and I just move it up 2. Move the whole graph up 2. Okay? Yes?
So for absolute value functions, can you go below the
Yeah.
x-axis?
Yes. Yeah, it will. The function can be below the x-axis if what I'm adding is outside of the absolute value. If what I'm adding is outside the value or subtracting is outside the absolute value, that moves the whole thing down. What's inside the absolute value, the smallest it could be, would be 0. But if I take 0, that's where it normally would be, and then I subtract 2, that moves going to move the whole thing down. Okay, does that make sense?
Yeah.
Yeah, what's inside the absolute value will never be smaller than 0. But if I have something outside, that just moves the whole thing up and down. Because I take 0 and subtract 2, I move everything down too. Okay. Horizontal shifts. What I have is inside. So the whole thing is moving sideways, left and right. Yes.
Oh, sorry. Did you say that when it's like plus 1 minus 2, it would be the parent function?
Yeah, the parent function moving up and down. Okay. The next one is my horizontal shift comes from being inside the function. X plus 2 quantity squared. Absolute value of x minus 4, when minus 4 is inside the absolute value. That gives us a horizontal shift. And the thing about horizontal shifts, they go in the opposite direction. 99% of the time, anything that is inside does the opposite. So x plus 3 squared, I don't move positive 3, I move in the negative 3 direction. I move in the opposite of what's there. Okay, the square root of x minus 4, my square root 1, instead of being starting on the origin, starts over at 4. And then goes up from there. Okay. Whatever inside, you go in the opposite direction. Outside of the function, you do the same. Inside, you do the opposite. That's 99% of the time, that's how it works.
Why does it do the opposite?
Okay, think about this. Normally on the square root of x, where would I start? What's the smallest value of x I can have? 0, right? And so my function for the square root would start here. But I do this one x minus 4. What's the smallest I can have for my function? 4. So what does it do? It shifts it over 4 units here and does the whole thing there. So I start at 4. When I put in 4, I get 0. When I put in 5, I get the same thing as when I put in 1. When I put in 6, I get the same thing as when I would put in 2 into the original equation. Does that make sense?
Yeah.
So this essentially moves my x that much. Okay? Yeah, this one changes my y values. This one changes my x values from the parent function. Reflections, those are pretty easy. Okay. It's either negative inside or negative outside. Makes it point up or down. Makes it change the direction it's pointing. Okay. Now, if my negative is outside, it reflects through the x-axis. Or sorry, yeah, through the x-axis. So like a parabola, instead of pointing up, my parabola points down. Okay. If it's inside, then it switches it so it reflects over the y-axis. Okay, which means it flips it this way. So if we're looking at the square root ones, okay. So if I have this one here, negative square root of x, it flips it down that way. If I have this one here, that's the square root of negative x, it makes a point in the other, go in the other direction. Because I can have x values that will work for the square root of negative x. X also has to be negative. So normally what would be true for 1 is true for negative 1. What normally would be true for 2 is true for negative 2. That's why it flips it across the y. And then stretch and compress. And stretch and compress. Stretch means makes it skinny. Compress means makes it fatter. Because the idea is you're stretching it. So imagine if I have a parabola. I've got an imaginary parabola in front of me. You all have imaginary friends. You can probably imagine my imaginary parabola, right? So I want to stretch my imaginary parabola. What am I going to do? I'm going to step in the middle. I'm going to grab it. I'm going to pull up. And I'm going to stretch it. What's going to happen to it? It's going to get skinnier. If I compress, I grab the sides and I push it down. What's going to happen? It's going to flatten out and get wider. That's why compression gets wider and the stretch gets skinnier. Okay. Oh my God, see below. Because this is very much more complicated.
I already did.
By 1 over.
Okay. So C is a constant. If that constant is outside of the function, if it's larger than 1, it makes it get skinnier. It stretches it. If it's between 0 and 1, and we're discarding the negative values. Negatives makes it point up and down. Negative has nothing to do with stretch and compress. Okay, and -3 in front is the same thing as a 3 in front for stretch and compression. The negative just means it points down. They have the same amount of stretch, just in the other direction, pointing down. Okay, so if it's outside, for example, if I have some c times x squared, some constant in front times x squared, that means it's outside the square. If the number I'm multiplying times x squared is larger than 1, it's skinnier, because what's it doing? It's growing that much faster. If I have 2x squared, that means I'm taking 2, I'm taking everything and it's twice as big. So when x is normally 1, with 2x squared, my answer would be twice as big. If I have 2x squared, it's normally twice as big as it, when x is 2, instead of being 4, it's going to be 8. And when it's 3, instead of being 9, it's going to be 18. It's twice as big, so it grows twice as fast. Yes?
What do you mean by outside the function?
Okay, so let's look at this one here. It's inside the function. This would be your constant times x squared. So if I multiply it by 2 and then squaring it, rather than squaring it and then multiplying by 2.
Wait, which is which?
Outside, I square first and then I multiply. Is it part of the squaring process or not?
Is what?
Is my constant part of the squaring or not? If it's not part of the squaring, it's outside the function. If it's part of the squaring, it's inside. If I have absolute value, is it part of what I'm taking the absolute value of or not? If it's inside, it works one way. If it's outside, it works another way. Okay. So I have a compression by 1 over c. So if I have 2x quantity squared, the 2 is inside. If I have 2x squared, it's a compression. It's a compression by the inverse of that. What they're saying is essentially this is the equivalent of that when you're looking at your stretching and your compression. If it's inside, it's a compression the same as if it was 1 over that on the outside. That's essentially what that is saying. Same thing goes here. If I have this, let's say I've got 1/3 x squared. That's the equivalent of 3 x squared. Yes.
So when it's saying like horizontal compress and like vertical compress, for the horizontal compress, would that mean you're pushing it down and it grows slower?
Really, you just have stretch and compression. It doesn't really, it does, horizontal and vertical doesn't really count for that. Horizontal and vertical is strictly where is it shifting up or down. You're taking the whole graph and just kind of sliding it one way or the other sliding up and down. And then the stretch and compression you're taking after you've moved it, are you making it skinnier or are you making it wider? Is it going to point down or point up? Okay. So your first movement is always the vertical and horizontal. And then you figure out, okay, once I've moved where my starting point is, so to speak, is it skinnier or wider? And does it point down? Does it point in the other direction that it normally points in? Okay, so it's a combination of those, but your shifting is generally what you address first.
So the horizontal and vertical doesn't play like a huge part. It's mainly just the stretch of the conference.
For the numbers out in front. No, actually, the horizontal and vertical shifts are actually more important. Because that's going to move your, on a parabola, that's what moves your vertex. That's what moves your vertex off of the origin, is the vertical and the horizontal. And that is actually much more important in the long run than stretching and compression. Unless you're talking very large numbers. So let's take a look at this. So this is our parent function. Okay, I've got a graph of the parent function up here. And I want to know, what do I do to it? What are the things that I have that are doing to this parent function? So I look at the +3. What does the +3 outside mean that I do to the whole thing? It means I go up 3. So I go up 3. That moves my vertex up 3. What does the +4 inside the square mean that I do? Move to the left 4. Okay. So my vertex moves over 4 and up 3. 1, 2, 3, 4. 1, 2, 3. This is where my vertex is now at. It's gone from there to there. That's what the 3 and the 4 do. Move it over 4 and up 3. Or up 3 and over 4 doesn't really matter. You stick it in the same place. What else am I doing to this? We got the negative, so it points down instead of pointing up. Yeah, this one here just means that I got a frowny face instead of a smiley face. When you're hand drawing these, the stretch and compression is the hardest thing to show. Because you're not going to be exact unless you punch in a few values and plot some points. I'm going to be perfectly honest. I really don't care about you being super accurate on that. If I'm asking you to hand draw a graph, there are a few things that are very, very important to me. Where's the vertex, if you have something that has a vertex to it? Where are your intercepts? Those are very important. Where are your maximums and minimum values? Those are important. Part of the reason the vertex is so important is that's exactly where your maximum and minimum values are. That's a huge thing when you're looking at a graph. Okay? How wide or skinny or how curved they are is very difficult to do accurately by hand. And even when you do it on your calculator, you do understand that your calculator is not showing exactly what the graph looks like, depending upon your window. If your window goes from -10 to 10 and -10 to 10, that would be a perfect square, right? But is your graph a perfect square? No. Your window on your calculator is not square. It's rectangular, so it's actually compressing it in the y value direction. It's still -10 to 10 from top to bottom. It doesn't take, it takes less to reach those points than does the y. So the x is stretched or the y is compressed depending upon how you look at it. So it's not exactly the same graph that you would get here. So it is a little distorted. There are ways to fix that distortion. They're not worth it. Seriously, they're not worth it. You have to adjust the windows, and there are numbers that will make it perfect. They're not worth trying to figure out. Just go 10 to 10 and 10 to 10 for 90% what you're doing here. Okay. So, is this exactly perfect? Do I have the exact same parabola copied over? No. Close enough for government work. Okay, close enough for government work. Okay. Give this one a try. Okay, this shouldn't take terribly long, however, it is a little interesting. What does the minus 2 do?
It moves it to the right.
Moves everything to the right, too. So instead of being centered on the origin, it's now centered over here on the point 2, 0. Okay. The 1/2 in front, that's the interesting thing. It compresses it. But what does the compression mean that I'm going to do? Normally, when you think about a compression, it makes it wider. So if it's a parabola, it makes it wider, right? But because it's a cube root and it's kind of laying out flat, what does that mean? Well, what it means here is it means it kind of flattens out. Every point that matches up with this would only be half as tall, because I'd be taking half of that. So instead of going through the point, so like here it goes through the point 1, 1. Normally it'd go through the point 3, 1, but it's only going to go through it half the way up. Every one of those points is only going to be half as tall as it normally would. So it just kind of flattens the whole thing out a little bit. And I know that's not perfect, but that's good enough for anything I'm going to explain. You want perfection? Use a computer. Okay. Do that one. Okay, how many of you shifted it over to the left 4 units? Wrong. No, absolute value still shifts the same way. Remember, inside is opposite, outside is the same. So it still moves in the negative direction. However, it does not move 4 units. Because if I take -4 and if I put -4 in here, am I going to get 0? No. Because what I have is my vertex here is what makes it 0. What's going to make that 0 inside is going to be -2. It's going to actually shift over here -2 places, and here's why. What's going to make that 0 inside? Because what makes it 0 is where your vertex is. What makes the inside 0 is the x-coordinate of your vertex. That's part of the reason why you move in the opposite direction. That helps you find it. -4 will not make it 0. -2 makes it 0. Because I have 2x in there, I have to kind of, it's not 2 times, it's 2 times x whatever. You have to think about it that way. So I have to move it over. And then because the 2 is inside, what is that equivalent doing? It's going to make it the same as having it be 1/2 on the outside, which means it's going to go like that. Okay. The 2 on the inside gives me a 1/2 compression as if it were a 1/2 on the outside. It goes in the opposite direction. Okay. Okay. So here's what you need to do. We have the parent function of 1 over x. I want to take that parent function. I want to move it 3 units to the right. I want to stretch it vertically by 5, make it skinnier. It's not exactly a parabola, but it's the same idea. And I want to make it go down 6 units. So, first thing I always concern myself with is my shifts. Okay. So to make it move 3 to the right, is that inside or outside the function? It's inside the function. Am I going to add 3 or subtract 3? I'm going to subtract because I'm going in the opposite direction. Going 3 to the right is where I'm going to positive 3. If it's inside the function, it's -3. So that means I'm going to have 1 over x minus 3. That gives us that right there. Okay. And the shift down 6, what does that do? How do I get down 6? I subtract 6. Inside or outside? Outside. So I go minus 6. That's moved the whole thing. That's taking the whole graph over and gone over and down. The whole graph's gone over and down. What has gone over and down in this case? Because it's 1 over x, right? So what that is my asymptotes have moved over. Instead of being the xy axis, basically I've taken those crosshairs and moved them over. My graph still fits within those 2 points. And now I have a stretch vertically by 5, which means it goes 5 times as fast, which would mean that I want to have
Didn't you change the top of the function to a 5?
Yes, exactly. You could do that on this one here. This would be 5 over x minus 3 minus 6. You could do that. If you give me either one of those, I'd be okay with that. Let me be perfectly honest, then that's what I'm looking for. I'm looking for this, I'm looking for this, I'm looking for that. That's like a 3-point question. Know me those 3 things. Maybe 4 if I feel like not being nice and giving you credit for trying. Okay.
That's what I live.
Yeah, partial credit isn't going to buy you a whole lot. Give B a try. Show up the rest of it tomorrow. Or, yeah, whenever we meet again. I don't remember which one is which. I just know that I meet one of you today, and then, or both of you today, and then every other day for the rest of the week. Okay, so reflected about the y-axis, compressed horizontally by 1/3, and shift up 3. So the up 3 means that I'm adding 3 outside. Okay, that's an outside one. That means it's not part of my equation. The compression means that I am multiplying the whole thing by 1/3 times whatever I have. Reflecting about the y-axis, that's the difficult one. Because if it's reflected around the x, that's easy. Just all my y's are change signs. But reflected about the y means all my axes change sign. This means I have negative x inside. So I have 1/3 int of negative x plus 3.
Could you put like brackets around the integer -1x or no?
You mean around this?
Yeah.
If you want to.
Okay.
You don't need to. Okay, we've done the integer function in here before. We had like the second or third day we did one. Okay, yeah, I can't remember that long ago. Okay, integer function, remember. Step function. So the integer function is the one that looks like this. Okay, if you make it plus 3, it moves it all up 3. If you make it negative, that means instead of having the dashes here, they'd be here, it flips this way. And then the 1/3 stretches it out. So each line would actually be 3 times as long.